we were discussing systems of curves and points lying scheme theoretically on a surface. So this surface, right, this picture in here, this surface is deforming in a certain linear system that parameterizes all these deformations. We are trying to count deformation invariant curves and points that lie on the surface as the surface deforms inside the ambient clavia. One way of doing this is to count sheaves which correspond to this picture. These are D4, D2, D0 branes wrapping the divisor, deforming inside ambient clavia. The sheaves are basically ideal sheaves of curves and points, but ideal sheaf as modules over the structure sheaf of the surface. We actually did discuss that there is these exact sequences that right here, if I look at ideal sheaf of system of curves and points on the surface, it sits inside the exact sequence below, and it's torsion-free sheaf on the surface. But if you embed it into the ambient variety, because surface is codimension 1, that sheaf will not be torsion-free in the ambient variety. It would be a torsion sheaf. Then we related ideal sheaf of the same curve with respect to OH modules to ideal sheaf of that very curve with respect to OX modules. We realized that functions on X vanishing on that curve and functions on H vanishing on that curve are related to each other by this term in here, which are functions on X vanishing on the surface. So this is the short exact sequence that we obtained right here. O of X twisted by the minus ample divisor H goes to ideal of curve as a subscheme of X, goes to ideal of curve as a subscheme in H, pushed forward into the ambient variety. Okay, so that's what it is. And now the statement of the theorem that I was trying to prove is that the moduli space of D4, D2, D0 branes is the moduli space of these quotient sheaves, push forward of torsion sheaves. There are two statements that we are trying to prove. One of them is that these have nice deformation obstruction theory as torsion sheaves. The other one is that even if I deform such a torsion sheaf, it's always going to be a sheaf, which again is ideal sheaf of a deformation of that curve inside the deformed H. A priori, this is not guaranteed, because if you take a sheaf, you deform it, it might not be ideal sheaf as an OH module anymore. It would be some line bundle, something else, which doesn't sit as a subsheaf of O of H. So this is a strong theorem. The other issue here was that this statement also implies that somehow this torsion sheaf moduli space is kind of parameterizing these as always stable sheaves. But that's not true, because we discussed about p-secure stability of these sheaves, and we discussed the situation where I allow the surface to break into two pieces, H1, H2, the curve Z breaking into two pieces, Z1, Z2, lying on H1, H2. Then the ideal sheaf, the sheaf, torsion sheaf supported on this whole system, this big thing, the sheaf which is on the union of the two, right? That, which is the ideal sheaf of this part, which is the Z ideal sheaf of Z1 union Z2 sitting inside H1 union H2, that can get destabilized by ideal sheaf of one of these things, Z1 inside H1 or Z2 inside H2 as sheaves. So this sheaf is not even stable. So its moduli space is ill-behaved. So we need to keep the objects we study always stable. We don't want any instability or instability appearing. So it's telling us that the criteria for our stability condition must also be altered, or else we cannot work with this moduli space. We could study moduli space of coherent sheaves which are of this form. Ideal, push forward the ideal sheaf of some curve inside the surface, but these are not gonna stay stable. So we need to change the stability, choose one with respect to which these are always stable. And this is exactly the significance of the exact sequence that we obtained. That if I, again, relate ideal sheaf of Z in H to ideal sheaf of Z in X, I know that O minus H sits inside this exact sequence as a kernel. Now, if I look at this part of this short exact sequence, it looks like a two-term complex. There is an object in the derived category with that representation given by O of X twisted by minus H going to I of Z in X. And this being an object in derived category can come with different stability criteria. And the one we are going to choose is the Joy-Song stability. Joy-Song stability says it's a stability condition for sheaves together with sections. You see, O to F is a section. As long as this sheaf is semi-stable in here and this section map is non-zero, that pair of the section and the sheaf, section means a map from O to F, is always going to be stable. Certainly, because ideal sheaves of Z in X are always, in fact, not only stable, but actually, not only semi-stable, but actually stable. And because this section map is also non-zero by construction, these are always Joy-Song stable. So this part of this is Joy-Song stable. And at least in this picture, this I dot is equal to that torsion sheaf. So even though torsion sheaf is not Gieseker stable, it is Joy-Song stable. So this is telling us that I need to study torsion sheaves which are identifiable with I dot and are equipped with Joy-Song stability rather. Okay, this is nice and it's really illuminating. However, I need to make sure that it's not true that I can always think of these as Joy-Song stable pairs, but it's under deformations, they are always going to remain as Joy-Song stable pairs. That means that if I deform, so this is actually saying that if I deform, I want to make sure that if I deform, push forward of ideal sheaf of Z inside H, it's always the same as deformation of OX minus H to I and Z in X. Well, the point is that because I lower star of Z in H is always quasi-isomorphic to this object I dot, then that immediately implies that deformation of I lower star of Z in H is the same, always isomorphic to deformation of I dot. These two things are in derived category, literally the same object. Okay, so that's clear. However, what is important in here is that objects in derived category are equivalent to each other modulo quasi-isomorphism. So if I have I dot, it could be equivalent to an object I dot prime if and only if there is some cap situation. There is some object A dot with a map to both of them, such that one of these maps is a quasi-isomorphism. And basically this morphism from I dot and I dot prime is a composition of these two maps. I call them P1 and P2, and this one I call it Q1. So quasi-isomorphism in derived category is always going through existence of a third object in the derived category. In fact, quasi-isomorphism is a weak notion of isomorphism. It means that if I dot is quasi-isomorphic to I dot prime, then homologies of I dot are going to be isomorphic to cohomologies of I dot prime. But that doesn't necessarily mean that, it does not imply that I dot is exactly meaning term by term, isomorphic to I dot prime. It could be that I dot prime is 20 terms long and I dot is 3 terms long, and then in the level of cohomologies, they have all the cohomologies isomorphic to each other, but they are not the same object. So why is this important? Because as object in the derived category, deformation of this torsion sheaf is always deformation of I dot. But what is not clear is deformation of I dot is always a 2-term complex, which is deformation of these two things. So question is I dot, an object in the bounded derived category of X, deforming always as a 2-term complex with representation given by OX minus H2 ideal sheaf of Z in X. That is deformation of I dot equal to deformation of OX minus H. Okay, that is what is not clear. Deformation of I dot could be some I dot prime which has 10 terms. That's the case, then you cannot say that this thing is always deforming as this 2-term complex. It's not true. Okay, so that's what we would like to prove. Now, in order to prove that, here is what we do. Okay, so it is turns out that deformations given I dot defined as OX minus H to I Z of X, deformations of the 2-term complex as a Joyce-Song pair. Joyce-Song pair is governed by X I dot comma ideal sheaf of Z in X, and deformation of I dot as an object in derived category of X is given by X I dot. Okay, hence we need to prove, one needs to prove X I dot I Z of H I Z of X is the same as X dot X I dot for at least I equal to 1 in the level of the first order deformations. Okay, the way you can show this fact is actually as follows. So you can consider the exact proof, consider the exact triangle. I dot goes to OX minus H goes to I Z of X. We know that I dot is equal to OX minus H to I Z of X. This equality is a map itself. So you can always say, oh, I dot goes to that thing. Okay, so this is an exact triangle. And then what you can do is you can apply homomorphism, apply Arham, for instance, I dot blank to this triangle, to delta. What happens is the following. So if you apply that, you will get Arham I dot Arham I dot OX minus H. Then you will get Arham I dot ideal sheaf that, and then you will get Arham with the shift by 1 I dot. Basically, you can put the thing in here and it keeps going. This will be shifted by 1. This will be the same thing again, shifted by 1. So as you can see, deformations of I dot as a Joyce-Song pair is here. This is the deformations of the Joyce-Song pair. And this is the deformations of I dot as an object in the bounded derived category of X. So cohomologically, these two things are related to each other, in fact. So given, if you look at this exact triangle, you can consider the induced long exact sequence of cohomologies here, cohomologies, which is saying that xi I dot goes to xi I dot OX minus H goes to xi I dot I of Z in X goes to xi plus 1 I dot goes to xi plus 1 I dot OX minus H, and it keeps going like that. Okay, for I equal to 1, we can see that for I equal to 0, in fact, we can see that we have x0 I dot goes to x0 I dot O minus H goes to x0 I dot I of Z in X goes to x1 I dot goes to x1 I dot O minus H, etc., etc. And in fact, you can actually show that basically you can show that these two terms, there is a so how do you want to show this thing? So one thing you can show is that you can show that this term actually vanishes. And then you can show that this morphism in here is actually going to be isomorphism. So that means that this term, this map between the two is going to be isomorphism. And that is enough because this is the deformations of Joyce-Song pair again, and this is the deformations of I dot in the bounded derived category of X. But why is this true? So x0 I dot homomorphism, this is just C actually. I dot is an unstable pair and this is just C. In terms of x0 I dot O minus H, if you want to show that that's also equal to C, one other thing you can do is the following. So let's write it down. So x0 I dot, this is x0 I dot O of X minus H. So I dot goes to O minus H, goes to ideal, just the ideal sheaf of Z inside X. So I can apply Arham blank O minus H to this exact triangle. If I do that, I'm gonna have Arham O minus H in here. Here previous to that, I have Arham ideal sheaf O minus H. in there. And then I will have, after here, I have x1 I z in x or x minus h, something like that. Okay, so now actually you will see here why we need it. Remember that in the various statement of the theorem, we made an assumption that this surface is pretty much ample with respect to the ideal sheaf. Hi of x, izx, twisted by h is vanishing for all I bigger than 0. So let me write this one over there because this is the key of this computation. So we have that hi of x, ideal sheaf of z in x twisted by h, is vanishing for I bigger than 0. So if this is actually equal to xi O minus h ideal sheaf of z in x, and this is vanishing for all I bigger than 0. Okay, so use Serre duality, and you will immediately see that this is going to be x2 O minus h I of z in x, which is the same exactly as this term, but x2, because I is bigger than 2, goes away. So you see, this goes away. This is 0 by that assumption. All right, that's good. How about this one? Use Serre duality here too. If I have, sorry, these are, by the way, just Hom and Hom, yes. If I have Serre duality, again, by Serre duality, this is x3 O minus h ideal sheaf. This vanishes too. Okay, so these two terms vanish. And this is just homomorphism from a line bundle to itself, and it is equal to C. Yes, so as you can see, this guy actually is C. So, so see, this is C, and it is isomorphic to this guy because this term is vanishing and this term is vanishing. So both of these are vanishing. So this whole thing is just C. On the other hand, by the stability of the complex, this whole thing is also C. All right. So I just proved that this whole thing is actually C, and this is C too. So, okay, let me rewrite this exact sequence again. So I had x0, I dot, which is C, isomorphic to C, goes to x0, I dot ox minus h, which is also equal to C. Yes. And that maps to x0, I dot I of z in x, and then that maps to x1 I dot, and then that maps to the other one, x1 I dot ox minus h. Okay, so far these two are completely isomorphic to each other. So this map between them is an isomorphism. Therefore, because the two are equal, then this map is an injection because, this just, there is no co-kernel, and the co-kernel, and basically there is this thing. So this is an injective map. So far as you can see, x0 I dot injects inside this one, this other term. If I can show that this term is vanishing or that this map is surjective onto 0, I am done, because then the map between them is both injective and surjective. That means it's an isomorphism. So all I need to do is what happens for this term in here, okay? So I can do the same thing again. So I have now x1 to take care of. So I have I dot goes to OX minus H goes to I of Z in X. I can apply blank O minus H to this thing and only look at it in the level of I equal to 1. So X 1 OX minus H comma OX minus H goes to X1 I dot OX minus H goes to X2 I of Z of X OX minus H. Okay, and then there is some terms after and there is some terms before, but I claim that this really we don't need. This is isomorphic to H1 of O of X, because again, this is a line bundle, this is X1 of O. Again, by the assumption that we had, if you remember, we are in a Calabi-Yau variety, which has this symplectic property. So where did we make that a statement? We made a statement, you see, this is the assumption that we had. H1 of OX is equal to 0 by the assumption. So by construction, this thing is isomorphic to 0 by construction. How about this term? Again, by Serre duality, this is X1 O minus H I of Z in X, which is, again, by this assumption in here, for all I bigger than 0, again, this thing is vanishing by assumption. This is the kind of analysis you need to do. So this complex is squeezed between 0 and 0. 0 maps to it and then gets mapped to 0. So this complex has to be itself, as a result, isomorphic to 0. So as you can see, this complex vanishes. So I am left now with an injective and a surjective map between these two things. So then X0 here, I'm looking at this, X0 I dot I Z of X is injected into X1 I dot, and that is surjected onto 0. Therefore, these two things are equal to each other. Therefore, the affirmations of Joyson pair are equal to the affirmations of I dot as object in derived category of X under the assumptions H1 of OX vanishing and HI of X, I of Z of X twisted by H vanishing for I bigger than 0. Are you with me on this?
Yes.
Perfect. So as you can see, beautiful algebra calculation and chasing the diagram, looking at the maps between these things, identifying deformations, you actually realize object in the derived category, which is I dot, of course, can deform into I dot prime, which could be a very different complex, but this assumption is forcing that I dot prime to deform exactly as the two-term complex of sheaves O minus H to I. Now, because these deformations are equal to each other, that is implying immediately that, well, this always deforms as I dot, and I dot always deforms as this one, so then that means this deforms always as a two-term complex, O minus H to I, and that is the proof of the theorem. Okay, so this proves the theorem, and so the corollary is that I dot deforms as OX minus H to ideal sheaf of Z in X. And since I dot is quasi-isomorphic, to push forward of the ideal sheaf of Z in H rather, yes, then push forward of ideal sheaf of Z in H, yes, is deforming as O of X minus H I Z in X. And hence the proof, the statement of the claim statement of the theorem is proved, i.e. Hilbert's scheme beta n of the universal hypersurface over the linear system of these hypersurfaces, which is the parameterizing the space of these guys, has a Joyce song parameterizing the space of these guys has a Joyce song moduli space. Moduli space of OX minus H goes to IZ in X. Okay? Clear?
Yes.
Excellent. Do you hear this small background music?
No, it's actually pretty low, so I can't hear it.
Ah, I see. Okay, so I put a little bit of background music. Anyway, but anyways, if you're not listening, hearing it, no problem.
No, it's okay.
Okay, so that's what it is. Now, now that we have proved that the relative Hilbert scheme, let's look at this statement again. Statement of the theorem is always important. Let's look at the statement. If H is sufficiently positive, which is that vanishing condition, Hi of X, I, Z in X, H, vanishing for all bigger than 0, this is what this statement means, then the Hilbert scheme is a locally complete moduli space. It means that not only in the level of the points in the moduli space, but also locally after deformations stays as Joyce-Song moduli space of pairs. Okay, therefore, because these always deform equally, then their invariance can be calculated by looking at invariance of the moduli space of Joyce-Song pairs. Okay, so I'll put this in here. So this is moduli space of these. So definition of invariance on Hilbert scheme of curves of class beta with n points on them sitting on some universal hypersurface which fiber-wise is members of the elements or elements of the linear system of surfaces on inside X. So that's what that Hilbert scheme is. Union of all Hilbert schemes for all possible deformations of H. So this the invariant is the following way. So suppose that H1 of XOX is vanishing. This is our assumption. And beta n and H satisfy the ampleness assumption as before, then Hilb beta n H this relative Hilbert scheme is equipped with a perfect symmetric obstruction theory. Of Joyce-Song moduli space given by, okay, symmetric perfect obstruction theory is an object in the derived category whose cohomologies captures deformations of Joyce-Song pairs. We realize that Joyce-Song pairs are given by these I dots. I dots are objects in derived category. And because of those assumptions that we made, their deformations, which are given by xi, I dot, always are the same as deformations of the O minus H and this. So this two-term complex. Yes. So, okay. So that's nice. So the Joyce-Song moduli space has this deformation. So let's say Joyce-Song moduli space is the set of isomorphism classes of OX minus H to ideal sheaf of ZX. That's what it is. If I call this one I dot, this deformation obstruction theory is a map. We discussed this before, is a map from E dot to the cotangent complex of the Joyce-Song moduli space. Yes. And this E dot, in fact, happens to be here, the one whose cohomologies capture xi, I dot. So this is going to be as follows. So if I have Joyce-Song moduli space, it is mapping to Joyce-Song moduli space mj of s. Let's call it mj of s, and this is a map to x. This is pi 1 and pi 2. Yes. So this is the moduli space of Joyce-Song. Okay, this is the cotangent complex. We discussed this before. Cotangent complex. Obstruction theory approximates cotangent complex in the sense that H0 of phi, this map between them is an isomorphism, and H minus 1 of phi is an epimorphism. We discussed this thing before. So what is E dot? E dot is exactly R pi 1 lower star of R hum I dot tilde with the shift by 2. So this Joyce-Song moduli space comes with the universal two-term complex. And if you look at homomorphism from I dot, that's basically what it is, the Joyce-Song moduli space. Okay? I dot tilde, where I dot tilde is the universal complex. It belongs to bounded derived category of X times the moduli space of Joyce and Song. It's living up there. Okay. All right. So that's what it is. And all right. So therefore, you can actually define a virtual class with this. Therefore, hence, this induces this symmetric and perfect obstruction theory. And theory induces a degree 0 virtual fundamental class on moduli space of Joyce-Song, and hence because moduli space of Joyce is locally completely isomorphic to Hilbert scheme, and hence on the Hilbert scheme as well. Therefore, define the new invariants. I'm going to call it invariants that depend on the ample class of that surface, the curve class, and the number of points. We define it as an integral on the very degree zero virtual cycle. Like that. Integral of 1, because this sits inside degree zero Chow homology of the relative Hilbert scheme. Okay. As an element of homology, it's degree zero. So invariant is given by integral of constant. Okay. Now here is a remark. Here's a remark due to work of Kai Behrendt on weighted Euler characteristics. These invariants can also be written as weighted Euler characteristics of the relative Hilbert scheme. Okay, so NH beta n is defined as weighted Euler characteristic of Hilbert scheme of points and curves lying on the fibers of this linear system. And the weighted Euler characteristic is basically the one that counts points in the space together with their multiplicity. So there is this constructible function, which is the Behrendt function. What it does is that it counts the multiplicity of the points. Because virtually Hilbert scheme is now realized as zero-dimensional subscheme, you see? Proving that the virtual cycle of the Hilbert scheme is degree zero is an important fact. It basically means that your moduli space virtually is realized as union of bunch of points with different multiplicities. Now, what Kai Behrendt showed is that if I have such a situation, there is some function that counts multiplicity of these points. For instance, one in here, maybe this is some n, maybe this is some m. And if I count multiplicity to points with multiplicity, that's the invariant of the moduli space. Okay. So that's exactly what it is. Another thing that I want to say is that, as we discussed before, if this is the Joyce-Sunk moduli space and this is the obstruction bundle induced by the deformation obstruction complex, this obstruction bundle has a section, and this section actually comes and meets the zero section, a bunch of points. Basically, the statement is basically saying that the point of intersection of section of the obstruction bundle with the zero section is bunch of points with their given multiplicities. Okay, that's what we are doing here. So if you count these with multiplicity, that is the invariant, counting invariant. Okay, so this is the constructible function on the Hilbert scheme of this relative Hilbert of this moduli space. Yeah. Okay. The reason that this becomes basically a deformation invariant, we also discussed before when we were discussing about counting points with multiplicity. Remember that A moduli space is always deforming. If the moduli space is virtually realized as 2 points, point 1 and point 2, and they deform and they become 1 point, if you just count Euler characteristic of this process, Euler characteristic in here, point 1 union point 2 is equal to 2, whereas Euler characteristic of this point 3 is equal to 1. And 2 is not equal to 1, so under this deformation, this number is not a deformation invariant. However, if you count things using multiplicity, point 1 and point 2 deforming and becoming a fat point 3 with multiplicity 2, Euler characteristic of P1 union P2 here is 2, and Euler characteristic of this point P3 with weighted by Barron's function, which counts the multiplicity, is also 2. So as you can see, these two numbers equal, so hence you get a deformation invariant. This is why counting points with multiplicity in this moduli theories produces for you infinitesimal deformation invariants. Okay. All right, so basically, that's that. So this is the definition of the invariance. This is the result of that important deformation theory arguments. Often it happens in the Gromov-Witten theory, Donaldson-Thomas theory. You look at certain moduli space, you do deformation theory of it, find some way that objects you are parameterizing deform as nicely behaving objects together with their own equipped stability condition. Here we found that Joy-Sung pairs are the accessory objects we need to look at. And then, because Joy-Sung moduli space has a nice, well-defined obstruction theory that induces invariance over the original moduli space. Okay, so that's one fact. So I think there is another fact I want to show, remark. Remember that, so now we are seeing that the moduli space, the relative Hilbert scheme which parameterizes eventually a set of isom classes of push forward of I, Z in H, this thing has become equivalent to moduli space of Joy-Sung locally, meaning under deformations also, which parameterizes isomorphism classes of OX minus H to I of Z in X. Okay, so therefore, invariance of this relative Hilbert scheme become invariance equal to invariance of moduli space of Joy-Sung. All right, that's good. The other thing that I would like to mention is the following. Now, if you look at the moduli space of Joy-Sung, one other thing you can realize, so it parameterizes isom classes of OX minus H to I of Z inside X. Now, there is a forgetful map, forgetting these section maps, the section S, which actually tells you if you forget that map, you are landing on the moduli space of isomorphism class of moduli space of ideal sheaves of curves inside ambient variety X. So this is the moduli space of ideal sheaves of Z in X. It's the Hilbert scheme of curves in X. And this is a famous moduli space. It's called MNOP moduli space. M stands for Maulik. We discussed about this. Nekrasov. This is Akunkov. And this is Panharibanda. Okay, this is really beautiful. So if I know what I would be losing by forgetting the section math, then I can find a relationship between invariance in here and invariance of MNOP moduli space. Seems like the two are just related to each other by this projective morphism pi. Now, the projective morphism is just a homomorphism from O to IZ. So let's consider this projective morphism. Let's see what pi is. Pi is from the Joy-Song moduli space to the moduli space of MNOP, takes an OX minus H to I of Z in X to just I of Z in X. Okay, this pi is parameterizing. Pi is parameterizing homomorphism O minus H to I Z of X. Yes. And this is H0 of I Z in X H, because I can put this in here and this would be hom from O to that, and that's just the H0. Remember that also HI of I of Z in X twisted by H is equal to 0 for all I bigger than 0. So it seems like pi is just a projectivization of sections of I Z of X twisted by H. Therefore, pi, the fibers of pi are given by, are parameterized all by projectivization of the space of sections of the twist of ideal sheaf of Z in X by the ample divisor H. That's what it is. It's a vector space and it doesn't change because it's flat everywhere, because higher cohomologies of IZ of X twisted by H all vanish. This is really remarkable because the dimension of these fibers do not change. So that means that invariance of the space upstairs are related to invariance of the space downstairs times dimension of the fibers, basically. That's right. So this implies immediately that NH beta N, which is the invariance here, this is NH beta N, because we know that the relative Hilbert scheme is locally the same as moduli space of Joy-Song. This is equal to, yes, Euler characteristic of the fibers of the pi, the morphism pi, times invariance of moduli space of MNOP, basically. Okay, so NH beta N, which itself is defined as integral over Hilbert scheme beta N HH virtual is equal to Euler characteristic of projectivization of H0 of IZX twisted by H times integral of the virtual class of the MNOP moduli space in the Calabi-Yau variety X. So this is remarkable because now we can see our invariants are related to ideal sheaf invariance. So we can calculate that. We can calculate, and turns out the Euler characteristic of this projective space, this needs to be calculated using Riemann-Roch. This is equal to the following integral. It's the integral of 1/6 H3 plus H squared times second taught class of X minus H times beta minus number of points. Okay, it's a topological number. Okay. Let's call it C. I'm gonna define it as C, a topological number. Topological number. It can be calculated. Okay, so this actually says that invariance of counting of curves lying on a surface, ample surface which deforms inside ambient threefold is equal to a certain topological number times MNOP invariance. So let's go give this MNOP invariance some number, some name, n of MNOP times n of MNOP. Okay. Very, very interesting criteria. So the surface is deforming, the curve is lying scheme theoretically on the surface, and the whole thing is deforming inside the Calabi-Yau variety X. There is some other problem where you had only curves deforming inside X, and that was studied by MNOP. So for those curves with respect to which this condition is satisfied, not all of the curves, we are not counting all the curves, we are counting only a few for which this cohomology vanishes, we can see that contribution of those curves is actually calculated from MNOP invariance, just times a moduli, just a topological number. MNOP invariance a priori counts all possible curves in X. We are not saying we are counting all of them. We are saying we are counting infinitely many curves, but only the ones for which this cohomology class vanishes. Each time that you fix a particular curve class, you can always find an ample surface with respect to which this cohomology can vanish. And then for that particular situation, you can calculate this particular topological number. And all you need to do is multiply that to the MNOP invariant, which depends on that curve class, beta. Okay, so this depends on beta and n also. All right, so this depends on beta and n. So this guy depends on h, and the rest, the other one depends only on beta. Okay. Any questions?
No, thank you.
All right. Yeah. Okay. So this is the end of the basically the class today. I think this is a good place to stop. We can study torsion sheaf theories and so on further in the second series of these lectures, but I think for now this is actually a good place really to actually stop the course.